Welcome back. So I've been doing a lot of shopping on Amazon because, I'm working here at home and I don't really buy a lot of things. But I finally decided to hit the purchase button on an item, and I bought a new black sweater here. So I hope it doesn't throw you off, because I know you're used to the old black sweater that I was wearing. But yeah, so this is chapter 11, three-phase balanced three-phase circuits. So in a generator, an industrial size generator for power distribution, we have three phases. So there's three coils of wire, and inside that coil of wire is a rotating magnet. And there's various designs, but that's a simplified idea of what's happening. So there's three voltage signals that are going to be produced, and each one of these is out of phase by 120 degrees, or a third of a cycle. So they look like this. They all have the same amplitude, but they're out of phase by 120 degrees. And the peak, if you take any given signal and go from peak to neutral, we call that the per phase voltage. And if you take any two phases and go from peak to peak, we call that the line voltage, or sometimes the line to line voltage, which I think is a more descriptive term, line to line. And this is for line voltage, use the term line to line, and for phase voltage, I like the term phase to neutral. I think that's more clear. And let's see. There's one more way to measure these, which is not obvious at all, and we'll look at that in a minute. But so one way to represent these voltages is as phasors. So there's three voltages, VA, VB, and VC, and they're out of phase by 120 volts. Now, if the motor's turning, or the generator is turning clockwise, then you're going to get VA, VB, VC. And if the motor's turning counterclockwise, then you're going to get this VA, VC, VB. This is just there to confuse you. We're not going to do this negative rotation. We're just going to do positive, because it's the same concepts. This is just serves no purpose other than to confuse you. So let's see. The voltages are balances. They have the same magnitude. They're off by 120 degrees. Okay. Also, the loads are typically balanced. Okay, there's going to be typically three loads connected up to these three phases in various ways, and we try to keep the loads the same. The loads on each phase the same. Okay, the line impedances are significant. That is, the wire from the motor to the load, whatever that load is long wire. So it's going to have a resistance that you can't ignore, and it's going to have a impedance that you can't ignore, because these wires are miles long, right, in power distribution lines. Okay, now there's this really interesting thing with the voltages here. I think it's equation 11.5 in the text, but like I was saying up here, if you go peak to neutral, that's the per phase voltage. And if you take peak, line to line between any two phases, that's the line to line voltage. Well, if you sum all three, okay, the sum of all three of these voltage, it works out to zero. Now the magic in the derivation verges on magical. It's in the text. It's pretty cool if you wanna look at that. But anyway, the sum of these three voltages come out to zero. Now the mathematical analysis is pretty cool on that, but you can sort of see that's the case in the phasor diagram, right? These three phases add to zero, right? Like if you took one phase that has a line to neutral, it's just one arrow going out. And if you go peak to peak, that would be like if you added this one plus this one, you're going to get this resultant right here, right? You're going to get this result, right? But if you add all three, you're going to get zero, right? So you can see that adding all three in the phasor diagram sums to zero, and adding two doesn't, and adding one, doesn't. But they do this mathematically in the text, and it's a trip. You might want to look at that. The other way to think about that these add to 0 is that the cosine of 60 degrees is a half. So like there's this one it has an x component and a y component, and then there's this one that has an x component that's exactly half, right? Because this is 60 degrees in here. So the cosine of that is half of this, and then this guy has another 60 degrees, and it's a half. So you've got half, half of the x component from this guy and half of the y component from this guy, and those sum up to cancel out this guy. And also the y components obviously cancel. So once again, it's easy to see that the sum of these three results to 0. It's easy to see that in the vector diagram. The book does it mathematically, algebraically, and it's pretty cool, but a real trip, almost magic. All right, so we have these three-phase generators. They're connected to loads in different ways. Now, you could go delta to delta, you could go delta to y, you could go y to y, and you could go y to delta. We're only going to do this. Okay, the other three exist in motors, generators, and in power distribution grids, and there's reasons for it, and there's many of them are just historical. But conceptually, we can get by with just this. So if you take a Y-connected motor, right? So there's 3 coils. Each one of these 3 coils is generating a voltage. So that's symbolized by this V little a, V little b, V little c, and they're 120 degrees apart, so they draw it like this. Although physically, it's a winding. The geometry is much more complicated, but we lay it out like this. Then the windings themselves in the generator are so long that you can't neglect the impedance, right? We have to model the impedance. So we model it with a resistor and an inductor. So this is the wire just in the motor, and there's 3 phases, so there's 3 of those impedances. Then there's the distribution line between little a and big A. This is the wire, the power line wire running for miles, hundreds of miles perhaps, across the country. So it has an impedance we can't neglect. And then it's connected to a load, right? And those typically 3 loads, or so this could be, we call this a 3-phase load. It could be one machine with 3 parts in it. It could be a really big motor, that is, with 3 phases in it, or this could be a model of a much more complicated distribution grid where we just abstract it down to these 3 pieces. In other words, this could be one neighborhood in a city, and this could be another neighborhood in a city, and this could be another neighborhood in a city, right? There could be 3 different subdivisions, but we try and, this could be 100 houses, ZA, ZB could be another 100 houses, ZCC could be another 100 houses. So on average, 100 houses are all going to be, watching TV and stuff. They're all going to balance out. So many people in here are going to be doing the same thing as so many people in here, and it all balances out. Okay, so once again, it could be a big city that we've broken into pieces, or it could be one giant industrial motor running a big stamping press or something, or melting aluminum or something, melting glass. We still have factories like that in America. Not as many as we used to, but we still have them. Yeah. Okay, so we draw this Y equivalent circuit with the generator over here, and then the load over here, and then the distribution lines in the middle. Now, an interesting thing happens because of this summing the voltage at this point. Like this here is how to say that? This could be grounded. This is the source node where we're starting, and then we're adding a voltage up to that, and we're dropping the voltage across all of these things. The voltage at this point is 0. So it's 0 here and it's 0 here. It's basically 0 across this neutral line, all right? Because of this sum of the 3 voltages, 0 magic, and then this is really, I could even throw a ground on here. You got to ground something, right? And that's what you ground. So you could ground this too. But anyway, because of this voltage across here, V sub n being 0, then there will be no current in here, right? Because the voltage at this node here is 0, so the current across here will be 0. So you can model this wire in several ways, whichever is most convenient. Now, there's another way that I like to think about this. There will be no current in this wire for a balanced load. That is, if these 3 voltages are balanced, which they should be, and these 3 loads are balanced, then the voltage here will be 0 and there will be no current in here. Which is sort of saying that the current is getting back through the other phases, right? Like, let's start here. So you've got VA, it's pushing current around through here and then down. And then we're saying that the voltage across here is 0, which it is. So there's no current in here. So how's the current getting back, right? The current starts here, goes up around. It has to get back. It gets back through these other phases, one of these other phases, one or both, right? Look at this up here. If VA is positive, at any given time, like if VA is positive, at least one of these other 2 phases will be negative. At least one of them. Maybe both. Depends on where you are in the cycle here. That's where the current will go. Okay, so it'll come up around here. It'll come back to this 0 point. So it won't go this way because there's no voltage potential to push it that way. But there's a negative voltage on one of these other legs. So the current will go out that way. So as long as these 3 loads are balanced, that's what's going to happen. The current's going to go around and back around through these guys. It won't travel through this guy. Okay, so you can leave this wire off if you wanted to. In real life, this wire isn't even here. Like, if you go look at a power line, there's just the A phase, the B phase, and the C phase. There's 3 wires on a power line. They don't even put the neutral line in there because there's no current in it. So that's pretty cool. I think that's cool. So let's see. Let's walk away from this for a minute and then come back to it. So the next page on these notes talks about line versus phase. So we're really talking about kind of this in here, this line to, or phase to neutral and then line to line. So let's just take the generator side of this thing. So we've got the 3 voltages and then the 3 generator impedances. And you could take a voltmeter and measure from the neutral terminal up to some phase, and you'd get V sub AN. So this is 0 to peak, really. Phase voltage, or also known as line to ground. To me, the term line to ground is less ambiguous than this phase voltage. I prefer this line to ground terminal. Okay, that's typically associated in a house with a plug that looks like this. Okay, we call that 110 house current, house voltage, or sometimes 120, depending on, I'm not sure why they use different numbers there. It's probably a typo that's just been carried on forever. But anyway, now if you measure between any 2 phases, like B to C or A to C, or the other one that's left, then, like, for example, B to VBC, we call that the line voltage, which I think is more precise to say line to line. Okay, so once again, I like the term line to line and line to ground, but the book and other people use phase voltage and line voltage. Anyway, this is the plug in your house. A 220 plug might look like this. There's about 14 different kind of 220 plugs. It's insane. A lot of that's historical. I mean, how many of these crazy things do you need? There's way too many. Like this, there's only like 2 or 3 of these, depending on the amperage. But for this, there's like a zillion freaking 220 plugs. Crazy. Anyway, So this is the relationship of the voltages, the phase voltage, neutral to peak, and the line voltage, line to line, in the phase diagram. Okay, so we're not going to do a negative. We're not going to do a negative. We're not going to do this negative sequence. We're going to do positive sequence. So anyway, here's the phase voltages, or neutral to line. Like AN would be here, and then here's BN, and here's CN. AN, BN, and CN are all 120 degrees apart. This is 120. Okay, and the phase voltages, this is all going back to the time domain, right? We have a peak voltage here, and then we have a phase line to line here. Okay, this is another sine wave, right? This VA is a sine wave. If you took this one minus this one, you just get another sine wave, right? With a 0 to peak value. You could plot this and see this. You guys could actually plot this out with some. I used Excel, or you could do it by hand. And if you plot this, you'll see these relationships in there. You'll see the phase shift, and you'll see the magnitude shift that we're going to talk about. If you actually plot VB minus VC. So, yeah, that's what you get. These things, I'm skipping the math derivation on this, but that proves, there's a math derivation that sort of proves what I was talking about here with just if you plotted these things. I don't know if you can see that, like right here. See, like if there's a certain point where the VB minus VC will be 0. So that's another sine wave starting at 0. And then there's a value, and there's a difference in here where these guys are maxed. I guess it could be here, maybe it's here, I'm not sure. But there's a point in time along in here where VC minus VA is max. And then there's a point of time where VB minus VC is 0. So it's VB minus VC is just one more sine wave. So that's sort of shown in this phase diagram. If you looked at these as just sine waves in the time domain, you'd see that AN, BN, and CN have a certain magnitude, and they're 120 degrees apart. And then you'd see another sine wave, VAB, which would have from 0 to peak, would have a different peak value. It'd be √3 bigger peak value, and it would lead its associated phase voltage by 30 degrees. So this is trying to show with a phasor what's happening in the time domain with the sinusoidal signals in the time domain. So yeah, memorize this. Brings us to page 3 on this thing. Somewhere around here. Okay, so this thing in page 1, this is how these are normally for a balanced 3-phase load. We have a 3-phase generator and then 3 loads that are all the same impedance. That's what we mean by balanced, is the impedance of each one of these is the same. If that's the case, then the voltage at this terminal will be 0. The current in here will be 0 because the current will be going back these other ways, and because the voltage potential is 0. So the currents in each of these other lines, the current in here, the current in here, the current in here, they're all going to be the same. They're just going to be off by some angle. Their magnitudes will be the same, and they'll just have different phase shifts. And that's true for the currents as well as all the different voltage signals. So we have a tool to simplify the analysis. It's called the single-phase equivalent. So instead of dealing with all 3 of these phases, since we know that basically the same thing's happening in all 3 phases except for some angles, right? Then we can just draw one phase. Okay, this only works when it's balanced 3-phase. only. If it's balanced, if the three phases are all balanced, the loads are all balanced, then they're each doing the same thing, just off by a certain angle, and we can just analyze one phase. So we call this the single phase equivalent circuit, all right? So we just drew the A phase here, and here's the VA generator voltage. This is the impedance of the generator windings. This is the impedance of the distribution line, the power line, and then this is the impedance of one of the three-phase loads. Okay, so this is a simple circuit, one loop that we can analyze, and then once we have, the voltages and currents in here, we know the answers to the other phases because they're off by various angles, 30 degrees, 120 degrees, all right? So one other thing that's good to introduce at this point is what happens in your house. I've been saying that back here, this could model a whole city where ZA is one subdivision, ZB is one subdivision, ZC is one subdivision. And so ZA could be 100 houses, ZB is 100 houses, ZC is 100 houses. So how does that look at a little lower level of abstraction? It looks kind of like this. So there's three phases coming out of the power plant. The neutral is grounded. Those three phases go out across the country. They could go, all three phases could go over to this big factory that has, say, one giant machine that uses all three phases. That could happen. Or you could balance the load like this. Subdivision A, subdivision 1, subdivision 2, subdivision 3. Subdivision 1 pulls off, say, A and B phase, and this goes to 100 houses. This is house 1. This is house 2, all the way down to 100. And there's a transformer in there. Okay, so we're pulling off A and B phase. There's a transformer. And then we saw this in chapter 10 or 9, where there's a center tap. I think it was chapter 10. Don't remember. There's a center tap. So there's two voltages available. There's peak to peak voltage. And then there's peak to neutral voltage going on, which is a little different than in here, because the phases after this transformer are 180 degrees apart, whereas up in here they're 120 degrees apart. And the three phases up in here are 120 degrees apart. The two phases coming off of the center tap are 180 degrees apart. Yeah, and then another subdivision of 100 houses may pull off of BC phase, and there could be 100 houses there, and then another subdivision of 100 houses could pull off of AC phase. So there's 100 houses here, 100 houses here, 100 houses here, and on average, the people in those houses are doing the same things at any given time, so the loads are balanced. Okay, so this is what I just did right here, by the way, is a delta connected load. This is A, B, C. We pulled off, but it would work with Y as well. But anyway, the loads are balanced. Okay, then one level deeper is what's happening inside of the house. There's if you go across the entire transformer, then you get 220 volt loads that run your anti-asteroid laser and your hot tub, and then you've got peak to center tap, which is grounded, so it's peak to neutral, and that's your so peak to neutral over here. That's your 120 volt loads, like your toaster and your TV and most of the stuff in your house. By the way, these need to be balanced, right? Some of your loads in your house are pulling off of the A phase to neutral, and some of the loads in your house are pulling off B phase to neutral, and you want to have approximately the same number on each side to keep your house in balance. But over 100 houses, this is all going to balance out on average. Any unbalanced current, by the way, any unbalanced loads on the way would go back through the neutral. If these three weren't ideally balanced, the remainder would go through the neutral. I have seen in some places of the country where there is a neutral conductor. And I guess if the loads were unbalanced, they would need that. And in Utah, in particularly, for some reason, perhaps they have unbalanced loads. Perhaps this is serving some other purpose that I'm not aware of. But around here, they don't have these. It seems to me, if you had an imbalance in these and you wanted to save money, you could leave off the neutral conductor and you could just send that. You could send that imbalance to ground somewhere, and it seems like it'd be cheaper than running an extra wire. But anyway, okay, one more page on the one more page. Math. That's what you're all thinking. Yeah, Prof. Russ, that's great, but where's the math? Well, here it is. This is what we need to solve these problems, in addition to all those diagrams over there. So we've got a three-phase generator, which we model as 3 voltage sources and 3 internal impedances in the generator. So if you measured at the terminals of the generator, you'd be seeing the voltage source and the internal impedance. That would be VAN, the voltage at the generator between neutral and A. And if you measured between any two lettered terminals here, I'll just say you're going to get the line to line. So got to cover up this stuff. It's too much stuff. So there's the phase voltage. For example, VAN is one of the 3 phase voltages. So they're all going to have the same magnitude, right? They're just going to be off by 120 degrees. So we can talk about V phi, or the phase voltage. It's a scalar because we're not really concerned about the angle. We know there's going to be 3 of them, 3 angles. So most of the time we're just concerned with the magnitude of this signal. So mathematically, V phase is going to be the magnitude of either V sub AN or the magnitude of V sub BN or the magnitude of V sub CN, right? These 3 will have the same magnitude. They'll just be off by 120 degrees from each other. Okay, then remember there's a current in here. Like this would be I sub A, for example. And there's a phase shift between the current and the voltage, right? In AC circuits, right? There's a voltage signal and there's a current signal, and they're off by some phase we call theta sub phi. This angle in here is the phase difference between the voltage and the current signal. So yeah, so that don't get confused between the voltage phase angles, these things, which have this 120, 120, 120, and 30, 30, 30 relationship. There's that. This is just relationship between voltages, just voltages. But remember, there's a voltage and a current, and those two have a phase shift. So don't confuse the interphase phase angles, that is the phase angles between the voltages. Don't confuse that with the current voltage phase angle. It's 2 different things. So we need that here. We need to think about theta sub phi, the phase difference between the voltage and the current. And keeping that in mind, we have a bunch of math we can use. So power in one phase is given by P sub phi is V sub phi I sub phi cosine theta phi, or just the phase voltage times the phase current. I sub A would be one of the phase currents. There's also I sub B, there's also I sub C. They're all the same. It would be like this except for current. And yeah, it's given by that. The total average power, piece of total, this is for all three phases, is just 3 times the phase power. So what we're saying is, just to be clear, we've got ZA, ZB, ZC. There's power leaving this guy. There's P sub phi power leaving this. The same amount of power is going to be leaving this if they're balanced. The same amount of power is going to be leaving this phase. Right? There's P phi power leaving that guy, and the same amount of power leaving that guy, the same amount of power leaving that guy. Now this is power. It's not going to have it. It's just the P component. So just the P component. So the total power for this three-phase load is just 3 times each of these P phis, and that's given by 3 times this above expression. Or you could use, instead of V phi, you could use root 3 V phi because this differs by the magnitude between these three is root 3. Seems like there's a 3 missing in there. Yeah, it seems like there's a 3 missing to me, but there isn't. If you do the substitution, if you realize that V line is root 3 V phase, so V phase is V line over root 3. So you put that in there, and you get V line with 3 over root 3, and you multiply the top and the bottom times root 3, and this becomes a 3, which cancels that. So the 3 comes up the top. It's funky, but it's correct. Yeah. So let's see. We're just doing y. So the source is a y and the load is a y. If that's the case, then there's only one current per phase. So the phase current and the line current are the same thing. Okay, they're the same. But for a YY connected load, which is what we're doing, the voltage and the phase voltage and the line voltage have this root 3 difference in there. And the opposite relationship is true for a delta-delta. So anyway, we're only going to do YY, and there's going to be one current per branch, so to speak, but there's going to be these 2 different voltages. There's going to be the phase voltage and the line voltage, but only 3 currents. If you drew this out, it would be clearer. If you drew out the circuit, if you drew out these 2 circuits and looked at that, it would be, in fact, I could just do it right now. There's a current here, a current here, a current here. There's just 3 of them and they're the same. But here there's a current, then there's a current. So there's more currents going on in here. Yeah. Okay, then there's some remember there's average power, P, and reactive power, Q. We still have that. So that we just went through the equations for the average power, P, then there's this reactive power, Q equations. Similar, except we've got the sign of theta phi in here. Okay, that's it. By the way, use RMS values for power. Then the complex power, we have a couple of formulas which are useful. So the complex power S per phase So just power leaving one phase of the load. So back to this, there's P leaving, but there's also Q leaving, right? There's a Q leaving each one of these dudes. Q. And altogether this is S. Altogether this is S. These two are S. So this is S per phase. And these are powers, just like these are balanced impedances. These will be balanced powers. So there's no phase angle between these guys because we're talking about power. And here we're talking about impedance. There's no phase angle between the impedances, between one impedance or the other. But that phase angle shows up in the power. It's a little freaky. See, this is theta sub phi. This is the phase angle between the voltage and the current. But that shows up in just the power calculation. Okay, it's a little freaky, but keep these straight, all right? This is theta phi is theta v minus theta I. It's the phase shift between the voltage and the current. That shows up in the impedance. We saw that in chapter 10, but it also shows up in the power here. So here it is. It's if you looked at it in rectangular form, it would just be the average power magnitude for that phase plus the reactive power magnitude for that phase times J. So the real part P and the imaginary part Q. And you could express it, or you could calculate it by this equation. It's V phi phasor times I phi phasor conjugate. And these will have a phase shift between them, V and I. Okay, and the conjugate is some weirdness that happens because of the math derivation. Use a little faith on that. You can also get the total power. It's just 3 times the phase power. It gets a little weird because we're dealing with a rectangular phasor here, but you'll see in the examples how we deal with this. But the total power for all 3 phases is just 3 times the per phase power, which is given by this expression, root 3v line, I line, angle theta. And then I'm saying scalar or vector as required because most of the time we're interested in this, which is this. And you could throw in the angle if you need it. Okay, I'll work some problems and you'll see how that works. All right. Thanks. Hope the sweater didn't throw you off.